This is a quick example of the bivariate regression presented in Chapter 8, starting with Table 8.1. So let's take a look at Table 8.1 that I've reproduced on the sheet here. We've got hypothetical data on hours spent studying, that is our X, and then our exam score, that is Y. So we're going to draw out our quick equation. So as exam score is equal to number of hours studying. That's our research hypothesis. And now let's use the regression line equation. Y equals A plus B times X. So when you're looking at this, this is somewhat confusing. Y is the value of Y, or your dependent variable. X is value of your independent variable, or of course X. And then B is the slope, and A is the constant, or the y-intercept. So when we're looking at the regression equation, we have the y, we know that's our dependent variable, and then we need to know the constant and then the slope of the data. So those are the two pieces of information that we're going to search for using this simple example to build our regression equation and be able to predict future exam scores based on the number of hours somebody studies. So when we're looking at this particular example, I am actually going to jump ahead to the scatter plot graph as well. And this is figure 8.3. But we can already figure out what the regression equation is. So again, we're trying to figure out the regression equation line for this particular problem or for this particular set of data. So the y equals our constant or intercept. What is our constant or y-intercept? The constant or y-intercept is the value of y when x equals 0. So exam scores are going to be equal to 55 plus, and we don't know the rest of this yet, and we know it's 55 because the value of the value of y when x equals 0 is 55. That is actually one of our data points. You will usually not get so lucky, and SPSS will tell you what your constant is. In this case, our constant is easy to figure out because the data tell us. Again, the constant, or A, is the value of y when x equals 0. And when you run a multivariate regression equation, you have a y-intercept when all of the values of your control variables are at 0. So the constant remains the same whether you have one independent variable or multiple variables. So when we're trying to go back to this example to build out the rest of our equation, we need to figure out what the slope is. So you can enter the data into a graphing calculator. Your book asks you to plot out this example, and that's what you would do with SPSS to run a scatter plot. So let's go ahead and do a manual scatter plot here for the data that we have. So along my y-axis, I'm going to have my exam scores. So 100, 0. So we'll do 50 in the middle, 60, 70, 80, 90. This is not going to be perfect. 50, 60, 70, 80, 90, 100. And then my x is going to be 1, 2, 3, 4, 5, 6, 7. So this is number of hours, and this is my exam score on the y-axis. So let's plot the data. So for 0 hours, we get a score of 55. So we'll do a scatter plot point. For 1 hour, we get 61. Whoops. So for 1, we want to do out here 61. For 2, we get 67. And I can start to see a pattern, right? So for every, let me go back up to the table. For every increase in hours studied, I get a 6-point increase on the exam score. This hypothetical is nice and neat to show you how this works. And I can keep plotting, and my linear relationship will show up on the scatter plot. So for 3 hours studied, I get a score of 73. 4 hours, 79. And then I jump up to 85. 91. And 97. This should actually be a linear line. So it's going to be a linear line that matches the regression equation. So now we know the slope. Because this data is pretty simple, we know that for every unit of increase in your x, the y value increases by 6. And I'll repeat that. The slope means for every change in value for x, 1 change in value, the slope is whatever the y changes by. In this case, it is 6. So our slope is positive 6. It could be a negative. So my direction of my scatter plot is going up and to the right in a positive direction. And again, it's because my slope is positive. For every 1 unit of increase in my x value, I get a 6 unit of increase in my y. And if we had a negative relationship, the slope would tell us the value by which y changes in a negative direction for every unit of change with the x value. So here we're working with a positive relationship. So our regression equation is exam scores, or y, equal 55. That's our constant, or our y-intercept, plus 6 times, and here it would be number of hours studied. So now I can plug in. If I can use this now to determine and predict what somebody's exam score might be if they studied a particular number of hours. So we're going to do, I'm just going to pick a number. So what would the exam score be if we had somebody who studied 5.5 hours? So I would do 6 times 5.5, whoops, 6 times 5.5. So the exam score for somebody who studies 5.5 hours would be 88. And again, I'm able to predict that because I built this regression equation using available data based on this framework of y equals a plus bx. So again, y is the value of your y, or your dependent variable. A is your constant, or your y-intercept, plus b, that's your slope, and we will be calling that the regression coefficient moving forward. But that is your slope, or how much y changes as x changes. And then x is the value of x. So again, that's the simple introduction to bivariate regression introduced to you in Chapter 8. And we looked at the table 8.1, and then we plotted out figure 8.3, and that's the end of our example.